this video, we take a look at another type of standard, or I should say basic electrical series circuit. And these circuits will involve, it would still have a resistor, but instead of having an inductor, it's going to have a capacitor. So we refer to these as RC series circuits. So let me just give you a little schematic of the circuit. So again, you have your resistor, and now your capacitor, again, depending on the symbol, the version of the symbol that you're using, this is what we will use for a capacitor. Not that the symbol is going to be of any huge consequence, but there. And then again, we have our switch, and then our voltage source, right? So our V of T. We have, again, we know what the R is, but let me go ahead and write this is the resistor, which does exactly what its name says. It resists the flow of current in the circuit. We have the capacitor. Capacitor there, so that's C, and then we have our V of T, right? So our goal, and let me just remind you that we're using I of T to represent the current at time t, right? Now, in an RC circuit, the way capacitors work and the way they function, right? And in fact, I'll just, again, very briefly say the reason why you would have components like inductors and capacitors is that they give you a way of storing energy. But the way they store energy is different. An inductor with the coils will store energy magnetically, right, in an electromagnetic field, whereas a capacitor will store it electrostatically. So like, you talk about getting a charge on your capacitor. In fact, that's another function now that will be of interest to us. And we're going to use Q for the charge. So this is the charge on the capacitor at time t, right? And again, it might not be something that you tend to analyze a lot in electrical engineering. However, it's basically going to be a means to an end for us, right? And we know that, so the units for current, we know that that's amperes. The units for charge, that's coulombs, right? And we know about resistance is in ohms, and capacitance is in farads. Let me put that there. So farads, ohms, and then of course volts. All right. So again, our goal, well, I'll say this. These are overarching goals. We want to find these two functions. Again, once you flip that switch and you have your current flowing through and you have your charge on your capacitor, what is the current at any given time? What is the charge at any given time, right? And what's nice is we will still use Kirchhoff's principle, but what we don't currently know is what is the voltage drop across a capacitor. Well, we're going to do that. In fact, I'll go ahead and do that now. So the voltage drop across a capacitor is, it turns out to be the reciprocal of the capacitance. So it's 1 over C, whatever that constant is, times the charge. So Q of T, right? There we go. So by Kirchhoff, we should be able to write down an equation that relates all the voltage drops with the impressed voltage, right? So by Kirchhoff, this is what we should get. Now, again, we did this previously. The voltage drop across a resistor is R times I. And now I'm saying the voltage drop across a capacitor is 1 over c times q, and then that should be equal to my v, or v of t, right? Could be constant. But I look at this, and this is a problem. This is not a differential equation. This is not a differential equation. Quite simply because there is no derivative here. I have my unknown function I have my unknown function q, I have a couple constants here, and I have again this could either be a constant or a function of t. So this is not a differential equation. It turns out, however, there is a nice relationship using a derivative between the current and the charge. So I'll tell you what that is. So since current is actually defined as the rate of change of charge, so dq dt, what I can do is I can replace I here with this derivative. So we have r times dq dt plus 1 over c times q is equal to v of t. And now what I have is a differential equation where the unknown function is the charge, right? So let me just kind of highlight the two key things here. So when we solve this differential equation, we're actually going to be getting our charge function. But really, it's the current that we want. I mean, it's not that you can't analyze charge. From what I understand, it's not really done a lot, right? But once we know the charge, by taking its derivative, we will get the current, right? So there you go. So we have another differential equation, and guess what? It is still linear. This is a linear differential equation with dependent variable q, independent variable t, and of course our r and our c will be constant. So we'll have nice constant coefficients on this side, and then possibly constant here, we don't know. Let's see what I have in store for an example. All right, so let's take a look at this example for our RC series circuit. And what I will do is I'm just going to write down the components. So we just kind of highlight. So we have an RC series circuit. And what do we have? So let's write down. So R, our resistance is 10 ohms. The capacitance is, and this is usually pretty small, let's say this is 10 to the negative 2 farads. And our voltage is now a cosine function, cosine of 2t volts, right? And let's say there is no charge, right? So there is no charge, so the initial charge is equal to 0. And again, charge is in coulombs, right? So that's the setup. And what do we want to find? So I'm just going to say find the charge as a function of t and the current as a function of t, all right? Let's see what happens when we dive into this particular problem. So let's start by setting up the differential equation. So we have 100 dq dt plus 1 over 10 to the negative 2 q, and then that's equal to 400 cosine of 2t, right? So there's our differential equation. We can put the initial condition right beside it. There we go. So there's our IVP. Now it's linear, but it's not in the standard form just yet. We would have to divide everything by 100. So dividing by 100, I get my derivative with the leading coefficient of 1, dividing 1 over 10 to the negative 2 by 100 will give us 1, right? Because this is 100. So if I divide 100 by 100, I'm going to get a coefficient of 1 in front of the q. And then remember, we have to divide the right-hand side as well. We have to keep our operations balanced, right? So we don't want our equation to become unbalanced. No, no, no. So we have 4 cosine of 2t, right? So there we go. So we can identify our p is 1. Doesn't get much simpler than that, but the q with the 4 is equal to 4 cosine 2t. That might pose a little bit of a challenge. Let's see. So our integrating factor is e to the integral of 1 with respect to t, so that's e to the t, right? And then if we multiply through by our exponential function, here is our differential equation. E to the t dq dt plus e to the t times q, and then we have 4 e to the t cosine of 2t. And then I can't not do it. I have to look for my my product rule in reverse. So if I know that I can call this f, and then this would be f prime, and then if I call this g, then this will be g prime. I think it's such a useful thing because if you don't see that pattern, then it means something was done in error previously, whether it's identifying p or integrating and finding your integrating factor. So I always recommend doing that, right? So the left hand side becomes the derivative of e to the t times our unknown charge function. And then we have our 4 e to the t cosine of 2t function on the right. So we have to integrate both sides, right? And then we end up having e to the t times q is equal to the antiderivative of 4 e to the t cosine of 2t with respect to t. And this is where, again, it gets a little messy because we have one of those tricky integration by parts problems where you have an exponential function times the cosine function or sine function, and you have to do a little bit of you have to do integration by parts repeatedly, then you have to do a clever use of algebra at the end. So let's go ahead and do that. So I am going to integrate so I'm going to integrate, so I'm going to choose let's see how we do this. Let's choose the 4 cosine of 2t as my u, and then just leave the e to the t as my dv. Essentially, it's not going to matter in the end, but let's go ahead. So I'm going to, so the trick with these is to do the derivative and the antiderivative twice so that you get back a cosine function, and of course you're going to get the same exponential function. So the first derivative is negative 8 sine of 2t, and then the second derivative is negative 16 cosine of 2t, and then when I integrate twice I get the same e to the t. So again, for these, it doesn't matter how many times I differentiate or integrate, neither of these functions will ever go to 0. They just keep oscillating. So the moment that the two original functions come back, we can stop our table and then let's set it up. But again, we're going to have to be careful because we don't have a 0 here. So we're going to have to be clever how we do it. So we are going to multiply these. So that's uv. We're going to multiply these, that's uv, and then I'm going to have to multiply and integrate these. This will be the integral. So let me write it uv, and then this is the integral of v du, right, when I multiply here. And then we also have to make sure that we alternate the signs. That ensures that we don't make any sign errors. So what does this tell me? Right? So this tells me that my original integral, so therefore the integral of 4e to the t cosine of 2t dt is equal to, right? It's the 4 cosine of 2t times e to the t. So I'll write it like this: 4e to the t cosine of 2t. And then I have this double negative here makes it a positive 8 e to the t sine of 2t, right? I need a little bit more room. But then I have to do minus, because this is plus minus, so minus now the integral of the 16 cosine of 2t times e to the t. So I'll put the 16, and then I'll do the, what am I looking for? Yeah, so I'm looking for, the e to the t, and then I have the cosine of 2t dt. Now, the way you handle the constant here, since I kept the constant inside, and I'm essentially, like I didn't pull the constant out. It might have been a little easier if I pulled the constant out, but I want to show you a way you could get this to work. Since we want to find the integral of 4 e to the t cosine of 2t dt, if I took out, to get a 4 out here, or not a 4 out here, but to get a 4 in here, I can factor out a 4. So it will look like this. And let me go ahead, just to simplify what I'm going to write down, I'm going to call this I. And then over here, if you notice, what I have is actually minus 4i, right? Because if I take out a 4 from the 16, I'll have the exact same integral in both sides. In fact, let me write that down, right? So we have the original integral here is equal to 4 e to the t cosine of 2t plus 8 e to the t sine of 2t. And then if I take out a 4 out of this one, then I'm going to be left with the same I on this side. So it's actually minus 4i, right? And then I can go ahead and solve for I. So therefore, I, so if I add, let me not skip this step. So adding 4i to both sides, I have 5i there. And then I will still have the 4 e to the t cosine of 2t plus 8 e to the t sine of 2t. And then technically, when you switch this back to an integral, so I have to divide by 5. So then my original integral is going to be this divided by 5 plus c, right? It's plus some constant. So this will be 4/5 e to the t cosine of 2t plus 8/5 e to the t sine of 2t, and then I'll go ahead and put my plus c. Technically, I could put my plus c here once I've isolated the integral, right? But then this constant will be slightly different from this one, dividing by 5. So regardless of it, the important thing is we now know what this integral is. So the next step, so e to the t times q is equal to, so now I'm going to write this down. So 4/5 e to the t cosine of 2t plus 8/5 e to the t sine of 2t, and I'll put the c1 there. That's fine. I don't have to. You could just go back to the regular c if you'd like. And then solving for, so here's our general charge function. So q of t, dividing everything by e to the t, the e goes away in this term and in this term, but then it will have to divide the constant. So we will get this 4/5 cosine of 2t plus 8/5 sine of 2t plus c1 e to the negative t. And again, this would be coulombs for your charge. Now, we were told that the initial charge is 0, right? So let's go ahead and solve for the constant and get the specific or particular charge for this response, right? So when t is equal to 0, q is equal to 0. So what's our equation? We got 0 there is equal to cosine of 0 is 1, so we have 4/5. The sine of 0 is 0, so that goes away. And then, of course, e to the 0 is 1, so I have c1. So then my c1 is negative 4/5, right? So here now is my charge function as a function of time. So it is 4/5 cosine of 2t plus 8/5 sine of 2t minus 4/5 e to the negative t, and then this would be coulombs, right? So that's our charge, and that's fine, right? I mean, you could analyze this function, you could talk about maximum charge or things like that if you wanted, but now our current, so I of t is the derivative of charge. So differentiating this function will give us our current function as a function of time. So the derivative here, when I differentiate cosine, I'll get negative sine, but then I also have to apply my chain rule. So I get negative 8/5 sine of 2t. And then differentiating sine gives me cosine, but then again chain rule, so I'll end up getting 16/5 cosine of 2t, and then again applying my chain rule and my rule for exponential functions, I get a positive 4/5 e to the negative t, and then the units here would be amperes, right? So this is now my current function for this particular RC series circuit. And I will just identify a couple things. Remember, previously we talked about, how the current is interpreted as the response, and we can look at the terms to see, what's the long-term behavior of each of these terms. Well, here, right, these two terms are periodic. Right? These terms are not going to go to 0. They're not going to go off the plus or minus infinity. So these two terms of our response is periodic, but this term with the e to the negative t exponent, right? This is a transient term. Right? So again, you can have so overall, right, in the long term, right, because remember, these go away. So then what we can say, if you wanted to say, well, what is the overall long-term behavior? So overall, I of t is a periodic response. Or I should say maybe in the long term, that's better, right? Because then by then this is negligible, doesn't affect it much at all. So it is a periodic response, right? So remember, you can have things like a transient response, but it's only this term that's transient. It's not the overall thing. You can have a steady state response. There's no steady state in this particular response because the terms are either sinusoids or exponential, so no constant terms. So there you go. A little bit more involved, just because of we have to do some fancy integration, but that's why that's why we're bringing out the big guns in the form of calculus that can help us analyze things where the the integral, for instance, might become a little bit more difficult. So we have all the tools that we need. We just have to, sometimes brush them off dust them off and use them quite a bit. So I think we should continue using some of these tools, and I'll do that in our next video. See you then.